Our next speaker is Geoff Bacon, who is a PhD candidate in linguistics, right? I didn't screw that one up. And he's also part of the TextXD2018 organizing committee, and he's going to be talking about sentence embeddings and structure-dependent tense.
Yeah, thank you very much. Okay, good morning, everybody. Thank you very much for being here. I really appreciate it. As Heather mentioned, my name is Geoff Bacon. I'm a PhD candidate in the Linguistics department, and I'm talking about work today that has been done under the supervision of my advisor, Terry Regia, in the Language and Cognition Lab. And I just want to, here at UC Berkeley, just want to give a quick plug for the Language and Cognition Lab, lclab.berkeley.edu, where we've been thinking a lot recently about semantic representation, so semantic sentence embeddings, word embeddings, the sorts of things I'll be talking about today, and in particular about how to make them more human-like, how to make them model human semantics better. And so, yeah, just a quick plug, check out the kind of stuff we're doing there. And the work that I'm talking about today is very much in that vein, and in particular, what I'll be talking about is how to assess whether popular methods of getting sentence embeddings capture main clause tense, the past, present, future, and so we're sort of assessing whether existing methods do well and to what extent do they accurately model the kinds of things that we want them to model. And so that's what I meant by probing sentence embeddings for structure-dependent tense. Here's a quick outline of the things that I wanted to talk about today. I'll start off with a brief introduction to the problem and motivate the problem and the history. I will show you the data that we, I wouldn't say collected, but we curated the data set that really targets this problem. Then I'll show you the experimental setup that we used and the details of the experiments that we're going to use to test whether these embeddings capture tense or not. And then I'll show you the results from baseline models and from perhaps more interesting models. And then I'll wrap up with some conclusions about what that tells us for designing models that represent semantics, so getting sentence embeddings. And just before I dive into the introduction, I just want to mention that I was conscious of the fact that here we have a diverse array of interests represented, and so I kind of aimed this at a really a bit of a high-level version of this talk, and to make sure that it's interesting and that I don't make you guys fall asleep more than yesterday. And so if you are interested in the more nitty-gritty details, I'm very happy to talk about that. In fact, I love talking about that. And so please ask me in the question time or offline if there are any questions about the details of the experiments and the nitty-gritty details that I can help you with. So with that said, I want to talk to you about getting sentence embeddings in natural language processing research. So a large swath of research, of current research in NLP, is concerned with getting universal sentence representations. I want some mathematical object that is going to represent everything I care about in a sentence so that later on I can do a whole bunch of downstream tasks. Maybe I want to do sentiment analysis. So I want to know whether this tweet is positive or negative. I want a sentence embedding that'll tell me that I can use afterwards to train a model on top of and say, yeah, this tweet is positive, this tweet is negative. But I also want that same sentence embedding to be useful for any other task that I want to do. Maybe I want to extract semantic roles. Maybe I want to extract out whether this tweet is racist or not racist or something like that. Everything that I care about, I kind of want to somehow plug into one of these representations. And by representation, I mean also the current most popular types of representations are vectors or embeddings, the same word. And so somehow I want to squeeze everything that I know into about this sentence into a 300-dimensional vector. A very popular, very prominent, and successful approach to doing that is to use any type of neural network, and in particular a recurrent neural network, to take a sentence and encode it into a fixed length vector. So take a sentence, whether it's 2 words or 100 words, and turn it into 300 numbers that represent everything I care about in that sentence. But what is interesting is that these types of models, these recurrent neural networks, a lot of the kind of core parts of language that we care about capturing inside these representations depend on syntactic structure. They depend on the hierarchical structure and how the words relate to each other. And sometimes the words relate to each other at a distance. These recurrent neural networks are sequence models and don't have that kind of bias inside them. And they're just reading from left to right and only know about like the sentences they've seen so far to the left. And sometimes you reverse the direction, you read from the right, but it's the same kind of idea. And so we have this kind of mismatch between the models that we're using that have this one type of bias, and then we know about the data that we care about has this other type of like structure going on. And so you would think that they do quite badly, but in fact, as in practice, and there's a lot of research showing, that they capture linguistic phenomena that depend on structure extremely well. Or at least in practical tasks, they do very well. And there's a whole bunch of research looking at whether they capture agreement, which is also a long distance has long distance dependencies. So they're doing quite well. So it's kind of surprising. One of the things, and then the way that people test whether this embedding or this representation has this linguistic phenomenon that you care about is a simple classification task. So I'm going to take this embedding, and I know that this one should be plural, and this one should be singular, and so I'm going to try and train a classifier on top of that to predict whether it's plural or singular and see how well that does. And that'll be my measure of how well this recurrent neural network was at, how good it was at capturing the information I care about. And that general approach is called probing. And so that's where the probing sentence embeddings comes from. One particular type of linguistic phenomenon that people have looked at is main clause tense. So asking the question, do these sentence embeddings capture main clause tense? So like past, present, future of the main clause. And in particular, recent work has shown that if you take a bunch of state-of-the-art neural network models and ask whether they capture main clause tense, the answer is they do it very, very well. They can get up to 91% accuracy on a test set that they collected. And in fact, even if you just take word embeddings, pre-trained word embeddings that were had nothing to do with this task in the first place, and you just average them together, you can get, on the same data set, 84% accuracy. So that's really good, right? Or at least that's what those numbers look like. Because this test set was, in fact, largely consistent of what I'm going to call easy examples. So let me show you what I mean by easy examples. So here's the kind of task that we're doing. We have Mary knows the correct answer. We have this sentence. We want to turn it into an embedding. And then I want to take that embedding and say, predict the fact that the main clause of this sentence is present tense. In this case, it's kind of easy because there's one word in here that has any kind of temporal information in it, the word knows. And so when I take the embedding for it, it's a pretty easy task to be able to just like find the word. You've averaged a bunch of stuff together, and a couple of the dimensions are going to have like temporal information in them, and they're going to be pointing in the direction of present tense or something, so it's not that hard. And then even in this example as well, Mary knows that the correct answer is Seattle because she lives there. So what I want to extract out is still present tense because that's the tense of the main verb here. But there are these two other verbs, I've kind of put them in blue here, is and lives, that are also present tense. And that's why I've got them in blue. They're not the main clause. They're not the information that I want to extract, but if you extracted them, you would also still be correct. And so 95.2% of the examples in the test set were like these two examples, where the majority, where the most popular, or the most frequent tense category, past, present, or future, in each test example was the majority category in the sentence. So you really don't need to know anything about the structure of the sentence in order to get the correct answer for these kinds of examples. Because you could even be paying attention to this word here, and if you have just a word embedding for that, and you can extract out that's present tense, and you'd still be correct. And so what I kind of care about is harder examples like this. Because she was there and did not look away, Mary knows who said they knew the correct answer. And if you could extract the fact that the main clause of this sentence is present out of this, then I would be really impressed. Because you have you have four other verbs here, that I put in red, that are kind of distracting you, giving you the wrong answer. If you can take this sentence and extract out the fact that it's present tense, that to me suggests that a model that created that embedding in the first place knows about the syntactic structure of this. Any questions about that? Okay, so that's the problem that I want to do, and I want to test similar kinds of models as the original paper on harder examples like this and see how well they do. So we're going to need some data to do that, and in particular we're going to need two types of data. The first type of data I'm going to need is unlabeled. I'm just going to train my sentence embedding model on unlabeled data. And a lot of the experimental setup that I'm using borrows from a previous paper, and so we're going to use this Wikipedia data set. It's a very common data set. You just take like English Wikipedia, and you extract out, we extracted 1 million sentences, and you get 25.7 million tokens in there. And I'm just going to train my sentence embedding models on that. I'm also going to do the same thing for French, Italian, and Spanish because I care about cross-linguistic generality. I don't just care about English. And then, so I can now train my sentence embedding model on Wikipedia. And then the next thing I want to do is have labeled examples of this sentence should be past tense. And so that's where on the right-hand side here, I have the universal dependencies sign. It's a large data set, fantastic data set in NLP research. It's got about at least 100 languages and thousands and thousands of sentences per language, annotated on a word level for individual grammatical properties. So tense is included in there, but also like gender and animacy and aspect and things like that as well. And so I have extracted out of that data set for each one of these languages between like 11,000 and 31,000 sentences where I then know that this sentence should be present tense or whatever. Cool. And I've split it into training and test, and I've called that my probing data set, and then the other stuff I've called my embedding data set. Okay, so the experimental setup looks just like this. I have my recurrent neural network in the middle here. I'm first going to train it on my Wikipedia data set, so it learns how to create these sentence embeddings. And then I'm going to use my universal dependencies data to get an embedding for each sentence. That's what these points here represent. And then I'm going to classify those points and try and extract out whether it's present tense or past tense. And I'm going to look at, I'm interested in these recurrent neural networks as a particular example of common models in NLP, but they're not state-of-the-art models. And so these ones that I'm comparing them against, for those playing at home, are like an LSTM autoencoder. They have 100 dimensions in both the embedding space and the hidden dimensions, the hidden layer. And I'm using dropout, and we can talk about the details afterwards if you like. But what I'm first going to show you is baselines of taking word embeddings trained on the exact same data and just averaging them together. Because they're my baselines of how well things can do. So here are my baseline results. For each language, you've got a different color here. And what I care about is the performance. And here I'm on the y-axis, I'm kind of showing the opposite. I'm showing the increase in error rate. So the higher the bar is, the worse this model is doing. And on the x-axis here, I have the number of conflicting tense forms in the sentence. So the number of distracting wrong answers there are in the sentence. And as you can kind of see, the general trend across every single language is that as you increase the number of distracting wrong answers in a sentence, the performance decreases, the error rates increase. And that's across all languages here. I should say that each one of these languages here has 50 sets of embeddings because there's some experimental variation in the way that you train these things. And so I have 95% confidence intervals here. And this is the height of this bar is the percentage increase over when there's no distractor. So again, the general trend is as you get more distractors, things get worse. And then now I'm going to show you the same results for the recurrent neural network model that we tried. And this is summarizing just one experiment because they take a little bit longer to train. And what we see is the same general trend, is that as you increase the number of wrong answers in the sentence, you get higher increases in error rate. Now there's an interesting, thing going on here with Spanish. Spanish is the yellow one. It's kind of like bucking the trend a little bit. And so, I don't have a great story for that, other than the fact that I think that I need to train, like this is, as I said, summarizing just one experiment. And so I would like to try it with like 4 or 5, and then see if I can average the results and see what happens. I think that's a better way to do things. So what do these plots really tell us? These are my conclusions. That we've done some multilingual experiments that suggest that these particular types of recurrent neural networks trained in this particular way, they do worse as the number of tense forms increases, the number of wrong answers increases, which to me suggests that if you care about generalizing in some kind of, whether you care about the theory or you care about a practical example, if you care about generalizing and being able to extract out the main clause tense, you need a different approach. You either need to train in a different way, you need a different model, maybe you need to use something more state-of-the-art. But in any case, there is the fundamental sort of sequential bias that is wrong for natural language in these models. And then the last thing is that we have a new data set that we've curated in order to test models that you might want to do this kind of stuff on. The one upshot, which is not really a result of my work, but you could figure it out from the original paper that I'm sort of responding to, is that if you, so they got really high results using just a bag of vectors, word embeddings averaged together. If you just, and they drew their test set, their examples, from a naturally occurring corpus. So that shows that basically most naturally occurring sentences in the data set that they drew from don't have many distractors in them. And so from a practical point of view, practical applied point of view, if that's what if you do want to do, if you want to extract out the tense, you actually can get away with just averaging vectors together, and that's pre-trained vectors, and that's going to give you like 84% accuracy or something. So that's pretty cool to know. So that's all I have to say. If there are any questions, please feel free to ask now or send me an email. And thanks for your attention. Cool. Yeah, John, right? Yeah, so the recurrent neural network model I was talking about, I can say a little bit more about it, was just a single layer autoencoder. So actually what's that's doing, it has 2 LSTMs in it. And the first one's reading in one sentence, and at the end spitting out a 100-dimensional vector. And then the other one's trying to take that 100-dimensional vector and recreate that sentence. As you're kind of pointing out, a more state-of-the-art approach is to have like a bidirectional 2-layer LSTM going, so one reading this way, one reading this way. And that would definitely give you an increase in performance. But that's sort of, I want to know, like, the model fundamentally does it, like, that reversing of the direction is just kind of getting at the same fundamental flaw that I'm kind of pointing out, yeah. Yep.
Hi, so that's pretty good to start research with analysis. I'm actually more concerned about the cross-language differences than about the bias issues by additional terms, because if you're looking for differences across countries, what you're actually detecting are differences across language, ability to predict in different languages and you've got problems, right? You've got systematic bias. So I guess I was wondering if you have any insights about why you're getting these differences across language. Initially I thought it was Romance versus Germanic, but actually if you go along to the right, then you get more similarity across countries.
Yeah.
So if you have any sort of
yeah.
how to minimize those differences.
In this picture, right?
Either, yeah.
Yeah.
Sure,
So do you mean more generally, like how?
Yeah. I mean, there seems to be a lot of difference between languages in both figures, both with the neural networks and the first model.
Aha. So I would actually, I agree with you on this one. There is a big difference, and I think that comes from the fact that this is only having one experiment. But actually here, I'm actually more inclined to view this as all the languages performing pretty similarly. One thing that is perhaps obscuring this, and so yeah, thanks for letting me point this out, is that the data sets are going to, for each language, it's going to have a different number of examples in this category here. So it's not the case that all these languages have 100 examples that have one distractor. And so I could actually control for that. Maybe that actually might help us to get more at the question of is there a difference here? And then if there is, then we have a bigger question to answer, yeah. Does that answer your question, or is there something else? Excellent, thanks. Yes, Joey. Yeah. Oh, sorry.
Okay, really interesting stuff. I'm wondering, when you're pulling from Wikipedia, were you pulling from sort of a set of sort of all articles, or were you looking at ones of only a certain level of quality scores?
Yeah, that's a great point. So I reduced the sentences to, they had to be between 5 and 70 tokens in length, and then which is what previous work did, and then I also worried about the quality of the sentences, the articles themselves, and so I additionally restricted to articles that had at least 10 sentences in them. So that was my way of saying, I don't want an article that is just a one sentence, because I can't really trust it, and this is rough heuristic for quality of the article or something. But I'm interested to hear what you think as well. Yeah.